east. Okay, so here's a rough drawing of problem 12. So at noon, the two ships are 150 kilometers apart. A is west of B. A is heading south at 35 kilometers per hour. B is heading north at 25 kilometers per hour. And we're trying to find how fast the distance between them is changing. Geez, was it a rough weekend or something? Where is it, buddy? Okay. So let's take it out on Monday's class. Okay. So let's see. And this, this leg follows that leg, right? So at least we can now write the Pythagorean theorem that c squared is equal to 150 squared plus, now this whole leg would be a plus b all squared. We want to know how fast the distance between them is changing, so our goal is to find dc dt. So if you got an equation that relates to them at any time, we can get the related rates equation just by taking the derivative. So the derivative on the left is 2c times dc dt. (150 squared is a constant, so its derivative is 0. Now we'll use the power of here. 2 times a plus b to the first power times the derivative inside. We'll have a dA dt plus a dB. Now we need A, B, and C. Was that an alarm or you just in the mood to hear a song?
Sent me something.
Did you guys know that song? Good, it wasn't just me. Okay, train of thought, come back. We need values for A, B, and C at a particular instant. So maybe we need to look at measurements of where these things are in 4 hours, since we started at noon. So let's let our ships do their moving. A is going south at 35 kilometers per hour. So let 4 hours elapse. And how far has A traveled? You want to multiply either, huh? 2 times 35 is 70, so 4 times 35 is 140 kilometers. And B? B's going 25 kilometers per hour. So 4 times 25 is 100 kilometers. We have dA, dt, and dB, dt. They're both getting longer, so let's keep them positive. And so we can put everything in. Well, maybe we need that number for C. So let's figure out what the length of C is when we have A and B. What do you mean the change of B is 0?
Oh, wait, what's your distance? What's your one?
B is, I only label things that are moving. This is changing and that's changing. Okay. Okay, so let's stop this picture at 4 o'clock and see where everything is. This is still going to be 150. A is gone 140, B is gone 100. So this length is going to be 240 kilometers. And now we're going to figure out C at that instant. Can't mentally do this. C squared is 240 squared plus 150 squared. So C is the square root of those numbers.
I got like around 283.
I'm just going to leave it like that. Now we have enough information to solve for dCdt. If you want, the 2's are just kind of in the way. There's a 2 on each side. Let's cancel them. Now let's plug everything in. C is that number. 40 squared plus 150 squared. Then we have dCdt. Then A plus B, again, that's going to be the 100 plus the 140. dA dt is the rate of change in A, that was 35. dB dt is 25. So I think I can do the arithmetic on the right side up to a point. This is 240, 30, 40, 50, this is 60. So dCdt is going to be that 240 times 60, and then I'm going to divide by that number in front of the dCdt. 240 squared plus 150 squared under the square root sign. And that'll be kilometers per hour. Okay. Oh, board. Is that blurry? Focuses. Focus. Focus, focus, focus. It's just blurry. Those are the steps that we always try to take. Set up an equation. First, label what's changing with variables. Then set up an equation that relates those changing variables. Take the derivative. You might need to look and see if there's an instant that you need all the values. So go back and diagram what's happening at that instant, and then substitute in all of the other unknowns. Okay.
So it's saying that powder forms a piece of clay into a right circular cylinder. She rolls it at height h, and the cylinder increases. The height h of the cylinder increases, and the radius decreases.
Okay, so it gets skinnier.
Yeah.
So H increases, R decreases. All right.
Wow, it's here.
Woo! You stole your thunder.
Oh.
You know what number this is first? Problem number?
Two.
2?
I just have a question about, it's asking you to solve for dHdt, but it's saying the volume stays constant. So
Yeah, so no clay is falling off.
yeah, so if you stay, or if you're like making a equation, how am I gonna solve for that if the other side's equal to 0 and I take the derivative?
Well, that's okay.
Well, then I would just divide everything with 0.
No, because you're finding how H is changing.
Yeah, but it's
Okay, so what's the volume of a right circular cylinder?
V equals pi r squared times h.
Okay, and so We want some sort of equation that relates dH dt and dr dt.
Yeah.
So we're going to take the derivative of this with the information that v is a constant. So what's the derivative over here?
0.
That one's 0. But over here, the derivative's not 0. Over here, we're going to take the derivative with the product rule, and pi is a constant, so I'll pull it out.
Oh, I wasn't doing the product rule.
That gum product rule keeps rearing its little head.
That's why.
So let's see what happens if we do the product rule. We've got the first times the derivative of the second plus the second times the derivative of the first. What's the derivative of r squared? 2r times dr dt. And then you can solve for this in terms of the other one, just by moving stuff around, right?
Okay, now I got it. That wasn't really.
Do we want to finish?
No, I think that's good.
Do you have numbers? Do I have numbers
Yeah,
anywhere? Or
numbers.
what does it want us to do? Solve for which one?
So it's the height of the cylinder is increasing at 0.3.
The units, what is it, inches?
Centimeter per second.
Centimeters per second. And we want to find,
You're looking for dr dt whenever the radius is 3 and the height is 10.
okay. Okay, so starting with this, take the derivative with the product rule. Volume's constant, its derivative is 0. First times with the second, second times the derivative first. Now we can put our numbers in. We're looking for dr dt. So this is going to stay unfilled.
You're looking for dh dt.
We're looking for dH dt. I thought you said h is increasing at 0.3 centimeters per second.
Yeah, sorry, no, you're
So
looking-
that one's dH dt.
no, you are looking for dr dt.
Okay.
Yeah.
Okay, so we're looking for this. And I think we have an H, we have an R, and we have a dH dt. So it's just a matter of filling things in now. So I have 0 is equal to pi r squared. R is 3. dH dt is 0.3. Plus H. H is 10. R is 3. And dr dt is what we don't know. And we're going to solve for this. So I'm going to divide both sides by pi. The pi is going to be 0 divided by pi, so it's gone. Okay. Divide by pi. So I have 0 is equal to 9 times 0.3. 3 times 9 is 27. So 9 times 0.3 is 2.7. Plus 30 dr dt. And so we'll move that over. Oh, right here.
Does it say what the radius is decreasing?
We're looking for how fast it's decreasing at that instant. So I'm going to subtract 2.7 and divide by 30. So it's negative because you were told the radius is getting smaller. 3 goes into both of those. So negative 0.9 divided by 10 would be a negative 0.09. And that's radius, so that's going to be centimeters per second. Yes. Did I lose a 2? Yeah, I did lose a 2. The 2 is going to be here. Let's make that a 20. And so that becomes 60 down here. And so now that's a 20. Oh, so now my number's not pretty. Put the 10 in there, and then I've got a 2. Pesky numbers. But you're gonna try all these all this weekend, those of you who are not asking. Yes, sir.
That was the plan.
More? Yes, sir.
Number 13,
13? Can I just read it to me, please?
a rope attached to a weight goes up through a pulley at the ceiling and back down to a worker. Worker holds the rope at the same height as the connection point between the rope and weight. The distance from the connection point to the ceiling is 35 feet. Suppose the worker stands directly next to the weight and begins to walk away at a constant rate of 3 feet per second. How fast is the weight rising when the worker has walked 10 feet and then 30 feet?
Okay. So let me get this idea. He's got a rope attached to a weight or to the ceiling, or has it attached?
Here's a picture of this.
I need that, because I can't draw it. I don't know where this weight is. So the weight is at the floor and the pulley. Okay. So here's the weight. Here's the rope. Here's some sort of thingy here. He's pulling. So he's walking away. This is going up. And that's coming out. Let's see one more peek at the picture. Yep, 3 things are changing. That, and that. Okay, all I got was how fast he's walking away. What else you got in there?
Yeah, those are the only two.
Those are the only 2 numbers?
Actually, then once like how fast the weight is rising, that was like 10 feet and then 30 feet. So it's like 2 numbers.
Okay, so this is rising at 10 feet per second? Is that what you said?
Oh, actually, never mind. It's like when the worker has walked 10 feet.
Okay, then this is 10. And are you told how fast the weight is rising, or we're trying to find that?
Yes.
How fast is this rising? How fast is the weight rising when he's walked 10 feet at a rate of 3 feet per second? Does that sound like what I'm looking for?
Yes.
And you said that he's at the same level as this?
Yes.
This is all the same? Oops, switchboards. Okay, so
And it says that the total rope length is like,
total rope length, this one or all of
I
this?
think all of it.
Total rope length is what? Try to hide a little number from you, did you? 70. Okay, well, let's see, we got 3 things changing here. Were we ever told how far away he was from the weight? Were we ever told this distance?
I think that's the 10 feet and then the 30 feet.
Well, it says suppose the worker stands directly next to the weight and then begins to walk away.
Okay, so this is, he's not standing far away at the beginning. So at some time he was standing right here. So that's what's going at 3 feet per second. right here. Okay, anyway, we got three things changing. Let's put three variables in there. So let's go with A, B, and C again. And now let's see what we got. Some initial value, or what is this 35? Is this, what is this number? Is that after he's done some moving, or is that initially?
That's the, yeah.
That's initially? Initially it's 35 feet. Then he starts walking away at 3 feet per second. And so when he's 10 feet away from the weight, we want to know how fast that weight is rising. So we're looking for dCdt. We have dAdt. It's equal to 3. Nope, we don't want dCdt, we want dBdt, right? The weight rising. I don't know anything about dCdt. I guess we're gonna have to figure that out with the total rope length. Right, if the total rope length was 70, then this is going to be.
Could you say C is 35?
Beginning of this.
Yeah, I started with C is 35.
I thought the 35 was this.
No, but because.
Oh, because it's 70. Well, I don't want to, I want to, since it's changing, right, it's getting longer. So I save that number till the end. So let's not worry about the numbers just yet. Let's write the equation that relates these three. That A squared plus B squared is C squared, right? But we don't want a C in here because I don't have a dC dt. So now let's substitute C out. So C is always 70 minus, or yeah, 70 minus whatever third B is, right? C is the rest of the rope. So C is 70 minus B. So I'm going to take that out, put 70 minus B all squared here. And now we can take a derivative. So we have 2a dA dt plus 2b dB dt. We're going to use power rule. 2 times the quantity to 1 power less times the derivative of what's inside. So we're going to get a minus dB dt. Are you okay with that? Again, I got 2's everywhere. You go ahead and cancel a 2. Make it a little bit easier to calculate later. Divide everything by 2. Now let's see what we got. At some instant, A is going to be 10. So I'm going to put the 10 here. dA dt is 3. B, we can figure that out. We will. So let's leave a gap for the B. dB dt is what we're looking for. Again, we're going to have to figure out B, so let's leave a gap here. And then we've got minus dB dt. Let's see if we can figure out what B's length is when he's walked 10 feet away. Shouldn't it be the same as the? He's going 10 feet away, hasn't 10 feet of road gone up? No?
No, because it's changing. It's a cosine or sine or something. But it's a
There's nothing about any angles. No angles given. Pull out any trig functions. Did I use 35 for what? But that's not, I need to know when that one's 10 feet away. So when they're 10 feet away here, I need to know how far up this weight has gone. Right, this is something, and then this is something. Sorry?
Probably throw the teacher through a loop too.
Well, no, it's not throwing me through a loop. I want to see what we got. It's something at 3 feet per second. And that's 10 feet. We don't know that, and we don't know that.
well, for the triangle, 35 is constant, right?
No, that's just initially.
I know, but like when you're thinking about the actual like triangle you're working with, for the angle and stuff, I think you do have to use triangles. I'm not sure.
I don't know why I would want to stick another function in here. Yes, sir.
So initially he's standing like right next to the weight
Yes,
and he's taking the rope that's the hypotenuse with him. And walking with him.
right. That's the way I understand it.
No, he's not initially standing right next to the weight.
I thought that's what the problem said.
So it's 70 minus 35.
He's-
So he'd be
he's
standing
doing similar
that
to
distance.
odds, so
He's standing right next to the weight.
So they're slacking.
Say that again.
if he's standing like right next to it,
Uh-huh.
and A changes to 10,
Uh-huh,
and then D changes, and C is still 70 minus B,
uh-huh.
it'd be like a similar triangle.
But initially, there's no triangle, right? Initially, it's a straight line. So that would have been nice if he had a triangle. All right, we're gonna get this. Would I be able to find B if I put the 10 in here? Let's see if we can find that out. Let's put 10 here and figure out what B is. Let's go back to this equation. Let's find B when A is 10. So we have 10 squared plus B squared is equal to 70 minus B all squared. I can go find that out.
I think we quite right actually. Because if you're looking at it, because on the point system, and no matter what, it's still gonna be 35 feet. Because if the rope is saying is changing, but still not changing the height of which I think that's only from the ceiling to the ground. So when you look in regards to the triangle, it should always remain 35 on the B side.
I think that's a way to do it. It's like
Yeah, except for this, my B is this. Not this.
I think it's a different way to do it,
That's-
but you have to like mix data, and that's just the wrong way to do it.
Right, and this is just 70 minus B.
There's an easier way to do it.
I don't think this is gonna be hard. We've got one variable in the equation. We can figure out B. We just keep going. I probably have to multiply this out.
Square root both sides.
The plus sign's kind of getting in the way. So I got 100 plus B squared, and I'm gonna square this. 7 times 7 is 49, with 2 zeros. Middle term is gonna be twice of that, so negative 140B plus B squared. So I got a plus B squared on both sides. Let's get rid of the B squareds. And now let's subtract the 4,900 from both sides. So my left side becomes a negative 4,800. And my right side just now has a negative 140B. So we can cancel the negatives, knock out one of the zeros. And so I have 480 divided by 14 is equal to B.
Like 34.3.
Decimals, I don't like decimals. Let's divide by 2. 240 divided by 7. So let's put that in where the B is. 240 divided by 7. 240 divided by 7. All right, I'm gonna do a little simplifying. The camera over. Let me erase this. Are you with me to that point? Numbers aren't gonna be pretty. We'll get there. So let's see, I've got 30 right here. Plus 240 divided by 7 times dV dt. Get a common denominator here. 7 times 7 is 49. So 490 over 7 minus 240 over 7. All right, I did my part. I got the over 7. 250. And that's times a negative dV dt. Let me put the negative here. Let's put our dB dt's together. I can move camera here. All right, I'm gonna put this, I'm gonna subtract it from the other side. So I have 30 is equal to a negative 240 plus a negative 250 is a negative 490 over 7 times dB dt. So when we divide by that, we can flip and multiply. So 30 times 7 is 210 divided by 490, and the whole shebang is negative. 3 times 7, you make it 210. Zeros cancel. 49 and 21 are divisible by 7. So negative 3/7 is dB dt. Does it make sense that it's negative? It's getting shorter, right? So the weight is, the rope length here is getting shorter at a rate of this many feet per, I lost my time unit, seconds.
I think I went theta because the force and the take would change with corresponding with theta.
But we're not given any, the angle doesn't change, or I guess the angle does change. We're not given any information about it. So I don't want to put more stuff in here that I could possibly deal with. Take the sign off and maybe try it without the sign. Didn't like that at all, huh? Turn all the numbers in the right places.
So much. That's weird.
bigger numbers. That would be-
Does it matter that it says like,
I think I see, this. That might be my problem. That should be.
Does it sit down? I think we did it and it only dropped with it. We would sit on the ground and fully push down.
Readjust my thing. B is going to be the height of the,
It'd be 35 minus 70 minus. 80.
yeah, I need something else in there. I need that 35 in there. But that's not true if B gets shorter. Because it doesn't make a triangle then. That doesn't make a right
Yeah,
triangle
it's-
then.
we're doing it so where the pulley
So
drops.
I've got to keep the pulley fixed, yep. So let's fix that. Let's rub all of this out. Think again.
That was testing us.
Oh, no, what is,
Remember, that's the thing that I like the least about math, is whenever you put so much effort into a problem, it's just completely wrong.
do you think that in real life, your first attempt is gonna work every single time?
Yes.
When you're an engineer and you think, oh, I think I'll try this, oh, look, it worked.
No,
Now let's just move on.
it's just like not knowing at all. Like, what went wrong. I mean, it's crazy. Oops. Oh, wow. It doesn't work.
Okay, so let's think again how I'm labeling these things. Initially, let's see, this is 35 feet. There's the pulley, there's the person, and there's the weight.
and it's 35 on both sides.
What do you mean on
Because
both
it doesn't
sides?
matter about the other side.
Oh, because he's got the rope in his hand?
Yeah.
That's fine. Okay, so now he's walking away at 3 feet per second. So let's see when 1 second has elapsed. So in 1 second, this person is 3 feet away. And now the weight is up in the air. And there's some rope here. So maybe I need to call this,
Yeah, I think you just solve for the actual rope length.
let's see, if this is, one of these can be B, one can be 35 minus B. So what is it that we're looking for? How fast is,
How fast is the weight rising?
so I'm gonna call this one B. And this then is 35 minus B. And this was C. And that one's A. But C is 70 minus,
Yeah, you have to flip the B. You should be the rope because it's 70 minus B. Or you can just change 70 to 70 minus 35 minus B, so 35. Or you can just make it as 35 plus B.
because that's 70 minus.
Yeah. Make it simple. My brain is too small for this.
Right? 70 minus 35 minus B is 35 plus B. Okay, and so yeah, I'm not gonna have a triangle all the way through.
I think you just solve it as if 35 is a constant, and then after that, use the 70 relation to 70 C and B to find that length after the entire.
If it's not,
primary
if it's not constant, I can't treat it as a constant throughout the motion.
But it is a constant because the height is constant. We're not talking about the rope at all. We're just gonna solve it as though the rope is infinite, and it doesn't
Okay.
matter the rope's length. And once that is done, you find C, and use C to find B.
Let's get the 3 feet out of here. That's a rate.
So you completely
Okay, so
ignore,
you're just gonna say that we're gonna get this right triangle here,
yes, just standard right triangle.
and then we'll worry, because that's gonna play a role right
Yes,
there.
because you just worry about that once you have C.
And let's give that a shot. We have a squared plus 35 squared. Let me have a think. A squared plus 35 squared is equal to 35 plus b squared. Okay. Make the derivative. 2a dt. That's going to have a derivative of 0. 2 times 35 plus b. First, derivative inside is dt. Now we put our numbers in. We cancel the 2 as we did before. A is going to be 10. The ABT is 3. We could go back and get B the way we did before. See, when A is 10, I have 10 squared plus 35 squared is 35 plus B squared. So 10 squared is 100, 35 squared, I don't know.
I'm not completely sure, but is that the same as the 70 minus B? Because I don't think we're using the other 35 minus as B.
I am. I didn't relabel my
'Cause you're-
picture.
Okay, you're, okay.
Okay, so I think 35 squared is 1225.
Oh, because you're just using 35.
So I had 100, so 1325 is 35 plus b squared. Let me get my arithmetic out of here. Now I can take the square root of both sides since I just have one number over there. So the square root of 1325 is 35 plus b. And so b is equal to the square root of 1325 minus 35. And so when I put that in here, that'll take care of the minus 35. So I got that. Then I have 35 plus this thing times dB dt. So those add each other out. I get 30 over here. I got the square root of 1325 here. Divide by that. That's going to be now feet per second. Let's try that one. Switchboards. Get some support here.
So can you explain why it is that the distance under the weight is B?
Hang on a second, I'm having visual difficulties. Can I just, because I labeled it as such.
But that still relates to the dB. Is it
Sure.
used to be plugged in? So why is it specifically we have to use the weight under B? as the,
I could have done the other one, but then this would have been the 35 minus b.
and it still would have worked.
Sure. Right, still looking for dB/dt, whether I have it here or there.
Just B was part of the formula, so.
Yeah.
It's the distance over the weight, distance over the weight.
I'm nowhere in here looking for the distance over or under the weight. I just want to frame that and I can figure out where everything is. So had I done this the other way, then this would have been a different measurement there. It would look a
Oh,
little bit
because the
different at that
35
point.
plus B is still dependent.
Yeah.
It would have been, it would have changed if you did it. So then it would.
So
it
the
is
way you
still-
label your picture at the beginning just helps you write the equation later on. It doesn't change the rate at all.
You get the 10.
Okay. That's kind of fun. I need to use the remaining time to talk about section 2.8. What was it, 8? We'll talk about linear approximation and the differential. We'll do some examples with that one. Started it last time, section 2.8. 3.8, that was close. There are two things in here. We need to look at how to make the linear approximation to a function. And how we can use the differential to approximate a change in y. And so essentially what we said, let me see, do I have the camera on the right board? I don't have the camera on any board. There it is. If we had some sort of function here, I drew it concave up last time. And we look at the change in f to 2 points. So if this point is x, I want a f of a. And then this point is a plus h, or delta x is what we need to use this time. And f at a plus delta x. I draw the tangent line to the graph at the ordered pair a f of a. The equation of that tangent line to f at the ordered pair a, f at a, looks like y minus y1 is equal to m, which is f prime at a, x minus x1. If I solve this for y, just by adding f of a to both sides, and that's the equation of that blue line there. And what we're going to use that for is, I have my x-axis here. This distance here is the exact change in x. This distance here is the exact change in y. We can use the point on the tangent line here to approximate a y value here. Suppose f has a very messy formula, and this might be a messy number. If I want to find the value of f at a messy number, I can just find the point on the tangent line at that messy number, and it gives me the approximate value there. So we're going to call this y value here the linear approximation to f at any x. This is our linear approximation. Then in the picture, the height that the tangent line climbs is the dy term. And what the dy approximates, that dy is called the differential. The derivative of f at any x, we're used to writing that as f prime of x, but we also were able to write it like this, correct? Dy dx is the same as f prime at x. When we take this and treat it as a fraction and multiply both sides by dx, we get our expression for the differential in y. The differential of a function is the derivative times the increment in x. The increment in x can either be written as dx or delta x. That's an easy number to compute. Delta x is the same as the differential in x since it's the independent variable. But dy is not the same as delta y. Dy is the derivative times the delta x. And dy is going to be used to approximate the exact change in y, where the exact change in y is the difference between f at that fancy number, f of a plus delta x, minus f of a. So there are the two things that we have. We have a linear approximation at a point, and we have a mechanism for approximating the jump in the graph by looking at the jump in the tangent line. Yes, sir. Well, dy is this whole thing. Dy is all of this. I mean, delta y. Dy, yeah, so if it was concave down, it would be in the other position. So maybe an example of something that has that shape of a graph would be something like y is 1 over x squared. 1 over x squared is pretty concave up when x is a positive number. F of x be 1 over x squared. Use the linear approximation to estimate 1 over 2.1 squared. That wouldn't be too hard to figure out 1 over 2.1 squared. 2.1 times 2.1 gives you blah, 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 then divide that into 1, and there you got it. Right? You can do that using arithmetic. But I can do it real quickly with using the tangent line approximation to this. If I think of this ordered pair as the one that occurs when x is 2, when x is 2, y is a fourth. So I look at the ordered pair 2, 1, 4, then I write the equation of the tangent line. And then I take my increment in x to be 1/10. So I write the equation of the tangent line when y is 1/4, x is 2, and then I'll get my derivative and put that number here. So that's the plan. Right? The equation of the tangent line at the ordered pair x is 2, y is a fourth, and change in x, which is the same as the differential in x, is 0.1. So we're gonna need the derivative to get the slope. What's the derivative of 1 over x squared? So it's a minus 2x to the minus 3, right? So negative 2 over x cubed. Then we need that number when x is 2. And I get negative 2 over 2 cubed. 2 cubed is 8. So I get a negative 1/4. Then the equation of the tangent line looks like y minus this 1/4 is equal my slope times x minus 2. If I solve this for y, I would add this 1/4 to both sides. And that then is my linear approximation. Let's just label it as such. So now we're going to take x to be 2.1 and find the value of this linear approximation at 2.1. L of 2.1 looks like 1/4 minus 1/4 of 2.1 minus 2. So that's just 1/10 in here. 1/10 times 1/4 is 1 over 40. Well, let me go to decimals. Maybe you want decimals better. 1/4 is 0.25. And then we said that was 0.1, so that's going to move my decimal one place. And so when I subtract that here, I get 5, 2, 2. Yes,
Sorry, at the very front should have y plus.
where?
Because it's y minus f of a.
My f of a is 1/4
Okay,
here,
okay, you're right.
and when I moved it over, it became a positive. But my slope is negative though. So what that's saying is that this number is roughly equal to 0.22.
We're done.
But the differential is just the derivative times dx. So sometimes we just are asked to compute it. Find the differential in y. If, say, y is equal to, swap boards here. Say x times the cosine of x. So this is what we're computing. So if it helps to remember, we just start by taking the derivative. We use this notation. Then we take the derivative with the product rule first times the derivative of the second plus the second times the derivative of the first. And then you solve this for dy. Just like that. Derivative times dx. Here's part B. That if y is equal to no, let's just check your derivatives. Arctangent of x squared. Step one, take the derivative. What's the derivative of the arctangent of x squared? One over u squared, so 1 over x squared squared. And then we take the derivative of the inside and get 2x. Now multiply both sides by dx. Let me write that as next to the fourth. Put the dx here, and there's your differential. So next I want to use an example that computes this as an approximation to the change in y. So let's just get a regular old polynomial going here. Let f of x or y, let's be a third degree polynomial, x cubed plus 4x squared minus 5x plus 10. I want you to approximate change in y as x changes from x is equal to 2 to x is equal to 2.05. So if you think geometrically, we've got some third degree polynomial, probably looks something like that. I don't know where x is 2 is. Right, third degree polynomial. But suppose x is equal to 2 is about right here. And then I'm going to move over to 2.05. Those are the x coordinates. There's a change in y as we made that change right there, and we're approximating it. So if I wanted the exact value of this thing, I would have to find f of 2.05 minus f of 2, where this is the icky number to calculate. Right? 2.05 cubed plus 4 times 2.05 squared minus 5 times 2.05 plus 10. I don't want to do that. So instead, so this calculation is yucky. So instead, I use the fact that dy approximates delta y. And dy is easy to compute. Dy is going to be the derivative of this thing times dx. The derivative of that is just 3x squared plus 8x minus 5. 3x squared plus 8x minus 5. Then we evaluate that at the nicer number. The nice number is the 2. And then we let the increment in x eat up the difference between these two numbers. Delta x is 2.05 minus 2. So we put the 2 in here and the 0.05 there, and that's our approximation to this. Three times 2 squared plus 8 times 2 minus 5. And then we multiply that by that increment in x. So I think even I can do this number. 4 times 3 is 12. 12 plus 16 is 28. 28 minus 5 is 23. And then I multiply that by 0.05. 3 times 5 is 15. 2 times 5 is 10. Plus 1 more is 11 with 2 decimal places. There's our approximate change in y.
So you just add that back to your.
I don't want to add it to anything. That's my change in y. Y roughly changes by 1 when x changes by 0.05. I'm short enough one for you.
Let me just leave it in x.
Where am I?
Solve that. I'm sorry.
Close. Link. An edge. Cube. It's measured to be 10 centimeters. But this cube expands because of change in temperature. So that edge increases by, I don't know, 0.01 centimeters. Right, how much does the surface area of the cube increase? In other words, x initially is 10 centimeters and it changes to 10.01 centimeters. Here I have a particular surface area. What's the area of a cube?
That's 230.
Area? Area?
Oh.
How many faces does a cube have? What's the area of each face?
It's a square.
There we go. So what you're asked to find is this number, delta A, which is the area at 10.01 0.01 squared minus this. Right? That's the exact change in area. But I don't want to do this calculation. So I'm going to approximate it. Okay? So I'm going to approximate this with dA. The dA is the derivative. It's the derivative of 6x squared. It's 12x times delta x. And I use the nice number here, the 10. 12 times 10. And the delta x I told you was 0.01. This calculation is much easier to do. 12 times 10 is 120. Move that decimal twice. So the surface area, surface area increases by approximately 1.2 centimeters squared by measuring by increasing the edge by that much. Okay? So if you did this calculation, you should be pretty dang close to that. But the point is, we don't want to do that calculation. We want to quickly approximate. Okay? Yes, sir.
So are we not using like a tangent line?
Well, I asked two different questions, right? There are two different questions. We use the tangent line to approximate a particular y. We use the differential to approximate a change in y. We're doing two different things essentially with the same concept. All right, so I think I put some web work up there for you with this. If not, I'll get on it sometime today. You turned in paper homework. I have graded homework. Come get it. Also, if you're still way behind, get caught up. Some of you have two of them in here, so make sure you get all of them.
We go ahead.
Yep, right here's the new stuff. So those, some of you are pretty far behind in submitting stuff. Get everything turned in. I get turned in midterm grades here.
Look good, Steve. I still keep my work.